Hi, my name's Jeff Denworth. I'm a co-founder of Vast Data, and today we're here to talk about DASE, the Disaggregated and Shared Everything architecture that's the basis for the Vast Data platform. DASE is the core of everything that we do and how we build distributed systems, and so we wanted to first start and explain how we think about distributed infrastructure and why the inventions that we built are so powerful for the AI era. And everything comes back to first principles that we build around. And really everything starts with essentially an idea that we want to simplify every single aspect of data and infrastructure management and processing. And so simplifying everything down to first principles thinking is entirely what guides our R&D team today. On top of that, we really want to embrace standards such that customers can bring their data and their applications to our systems, and essentially they don't need to refactor everything. And so as an enterprise infrastructure, what happens is that your data essentially just becomes ready for the next generation of AI as opposed to having to build different systems that you use for AI processing. And finally, ownership is also everything, where we want our customers to own their data and be able to deploy that on their infrastructure of choosing. We don't make these choices. We're not the stewards of infrastructure or data for our customers, and they can build their own zero trust environments as they see fit. So what we're doing is we're building AI-scale distributed infrastructure, and I'm purposely not saying storage right now because there's a broader definition in play here. And as we think about data stores as they've been built over time, and we looked for opportunities to invent, we first started to think about storage arrays that were kind of popular in the early 90s. And these are systems that had certain performance properties that were really designed for the transaction processing era. But as data sets started to scale, people started to invent new types of systems. And today, when we talk about scale out, we typically talk about another type of systems architecture called direct attached shared nothing, where you have commodity nodes that are built with some internal storage, and you build out clusters of these systems from a lot of the nodes. And so we went and root caused, kind of how we got here and how the scale out era of today has been built. And everything goes back to a paper that was written by Google and published in 2003. So roughly about 20 years ago, the first shared nothing systems were introduced to the world. And since that time, there's been hundreds of billions of dollars of systems that have been introduced into the world that kind of are in the spirit or mirroring that style of architecture that Google brought. Everything from our hyper-converged systems to our scale-out file systems to our databases and everything in between, even object stores, are all built of that style of Google architecture. That system was really built for a style of processing that is less and less relevant today. If you think about the early design points that Google laid down, you're talking about thousands of nodes that manage hundreds of terabytes. Today, you can put 100 terabytes in just a single node. And so some of the design points are less relevant, but more importantly, some of the challenges that these architectures have created have become more poignant. Let's think about these through the lens of just looking at a standard server, right? A server that has some processors that run the logic of the system, has some memory to hold things like cache and metadata. Batteries are there to make sure that if the server fails, you don't lose the data that's in RAM. And then you have some storage devices, hard drives or flash, or maybe a mix of both. And as you think about building out these systems, one of the things that becomes very evident is that consistency is a real challenge as you start to build distributed systems, because all of these nodes need to stay in communication with each other. The term is called shared nothing, but in reality, they're all sharing all sorts of information. They're sharing metadata, they're sharing locks, they're sharing updates to caches, and that becomes an amount of internal traffic which can be really challenging, particularly as you start to grow out infrastructure. And so as you build large clusters, what happens is there's so much internal traffic running in the system that it really slows these systems down and makes them unable to respond to the external application traffic. There's a law of diminishing returns that kicks in, and for that reason, you still have storage arrays, and array-style systems is popular for transactional I/O, and then you use for analytical I/O, or you use for scale-out content management, distributed shared nothing systems. But the problem becomes that if you look at this through the lens of just a storage environment, then that becomes a pretty myopic view. In reality, this principle applies both to classic storage systems, but also to classic database and database management systems. If I use kind of standard storage arrays like NetApp and like AWS's S3 as examples of both scale-up and scale-out architectures, you can equally mirror those against database systems. Scale-up systems like SQL, scale-out systems like Hadoop mirror the same architectures that have been popularized in the storage era. And in both cases, you have to choose. You have to choose between if you want transactional I/O or if you want scalable analytical I/O and capacity management, but you've never been able to have one in both. For that reason, we started to think, okay, what else can be done? And then we started to look at how these nodes were constructed, and we equally realized that there was a series of compromises that customers had to make. You have systems that are designed for high performance with a lot of CPUs and some high performance storage devices inside of them. Let's call those your performance nodes. And then you build out other types of nodes because those performance nodes were never designed for low cost. You build out other types of nodes to save money. So you have hybrid nodes that have maybe a mix of solid state devices and hard drives. You have archive nodes that are mostly hard drive based. And then customers need to make the unfortunate decisions about how to prioritize and deprioritize their data based upon how they want to save money on their infrastructure. And so there's never been one solution to solve all the problems of performance and capacity. And if you roll all of this up, we realized that there was a lot of opportunities for invention based upon all the challenges that we saw with that classic shared nothing architecture, which didn't solve for all of the problems of scale up. And so we decided to build beyond the state of the art. We decided to build a next generation systems architecture. We believe the first major systems architecture that's been invented since Google laid down their architecture for the Google file system in 2003. And it starts with an approach that we call DASE. DASE stands for Disaggregated and Shared Everything. And it starts by decoupling the CPUs from the underlying storage devices and building systems that are interconnecting CPUs with storage devices over next generation commodity low latency storage fabrics. And so now you can have an independent number of CPUs that access an independent number of storage devices, and you can build large clusters where every CPU can see every single internal storage device over that fabric that I mentioned earlier. And so if you open up one of the processors, you would see every single storage device in the cluster mounted to a container that runs our software, as if it was direct attached. But in reality, no CPU has authoritative ownership over the data at all. All the CPUs can see all of the data. And so it's a new approach to managing state within the system where we've essentially disaggregated functions and state, logic and state. Just like a data center scale von Neumann architecture, you can basically build a distributed system that's not built from partitions, but rather a collection of CPUs that all see one global shared volume. We had to work a lot on a data structure that basically made it possible for all these CPUs to access the same shared state without having to coordinate with each other. And when you get there, you basically have a system that's designed for crazy levels of parallelism. Parallelism that's required to take these systems beyond the classic use cases to also support applications like high-performance computing, like distributed databases, and of course, next-generation AI applications. So beyond just building a system that's designed for high degrees of parallelism, as you start to think about building systems that can scale to hundreds of petabytes or even exabytes of data, resilience becomes a key design point that we think about. And we definitely embrace the cattle versus pets mentality, where we're on the side of cattle, being able to lose whole collections of infrastructure without essentially losing any sleep on that. The CPUs that run our software, they're independent from each other. And that means they're not talking to each other. No code issues or no bugs get propagated to the other machines in the cluster because there is no interdependency. But it also means that we can build large distributed data protection schemes across storage devices where you can essentially protect from an SSD failure, from a node failure, even a rack level failure. And so now you can have whole collections of processors disappear and you don't lose any sleep over it. You have whole collections of storage devices disappear and you don't lose any sleep over it. It's a system that's designed to deliver absolute levels of uptime. In the field across our estate of customers, we're just a touch under 6 nines of availability. And so what that means is that customers are on average down for less than a few minutes a year, and we're building systems that scale into the hundreds of petabytes range. And that is really never been seen within a distributed systems architecture where you can get to that level of scale with that level of availability in a single systems architecture, but that's what we designed for from day one. This new approach allows you to scale to tens of thousands of CPUs, exabytes of low-cost flash infrastructure, and we apply a number of efficiency algorithms against your data such that you can really afford one tier of flash for all of your data. Now that you've got this kind of the basis for your data store, the next thing that we wanted to do was to essentially build a mechanism that allowed us to manage data better than what you've been able to do in the past. And so that starts by building a system with very deep persistent write buffers. This today is implemented in storage class memory, and it's basically a landing zone or a shock absorber for the system that allows us to place data into a part of the system before the data gets flowed down into very, very low-cost web-scale flash. And so this buffer, first and foremost, allows us to classify data according to its life expectancy. That allows us to preserve the SSDs that we work with such that you can field them up for up to a decade. And so we basically, as data flows into the system, we're categorizing it according to that life expectancy. The system basically has a counter or a transaction counter that's running all the time. And that allows us to build consistency points in a log-structured manner as data flows into the system. So it's a write in free space architecture. And as we're writing into the system, we're just creating points in time. Those points in time allow us to essentially add a few additional services on top of the system that don't take away any performance. The first of which is a global exabyte scale distributed snapshot engine. So snapshots are always delta-based. The system's right in free space, so we're not copying any data. We're not copying any metadata. We're just creating a pointer that says, reserve the snapshot. You can snapshot across the whole system at any directory depth, and you can have up to millions of snapshots running in the system. So it's a great way to manage data and protect data over time. We've added additional functions so that you can do things like preserve your snapshots even in the event of a ransomware attack. And that snapshot engine becomes the basis for all sorts of other types of data manipulation that we do. First of all, it becomes the basis for a distributed replication engine where you can do delta replication to n number of sites without taking any performance away from the system. It also becomes the basis for data cataloging, where we're basically taking snapshots in real time of the system and adding all of the new writes, all the files, all the objects, and even the tables that you write, and we're articulating those in a data catalog that you can go query upon. It becomes the basis for all of our efficiency, so we can do things like protect against the endurance problems of low-cost flash. We can build really wide write stripes that save you money on data protection. And most importantly, we can run global compression mechanisms by correlating data at global scale before that data gets flowed down into low-cost flash. And I'll talk about that in a moment. And so now we've got this distributed state management system with all sorts of interesting functions that happen, and it's designed for extremely low cost. The architecture allows us to think about new styles of deployment, new styles of composability for reasons that none of the machines within our system talk to each other. And in the earliest days, we realized that that can be applied to making the system composable. Now you can collect machines that run our software, the containers that run our services, and you can create them into pools that can be allocated to different noisy neighbors such that one neighbor won't talk over another by virtue of the fact that they have their own dedicated infrastructure. But on top of that, these pools allow us to also interconnect the system into different physical networks within a data center without having to put all your storage on that network. And so it's a nice way to build site-wide infrastructure while not having to put all your storage on every network or not having to worry about the noisy neighbor QoS problem that has kind of held infrastructure back from deploying in that type of fashion in the past. Now, on top of that, as we think about building that core infrastructure that's used for all of your applications, how expandability works is a core part of how we think. And the interesting thing is that we realized in the earliest days that we could abstract the different idiosyncrasies in hardware from multiple generations of infrastructure away from the user experience. And so basically with this system, you can essentially build multiple generations of hardware in the cluster using multiple generations of flash as well as multiple generations of CPU. And we can essentially make it such that there's a balance of performance and capacity that's maintained, even though we're building from different parts over time. At the flash level, it makes a lot of sense, right? If you think about flash devices, as you evolve them over time, they grow both in terms of their performance capability and their capacity. As we add next generation devices into the system, that preserves the balance of performance and capacity such that customers don't see a difference from multiple generations of hardware. Same is true of CPUs. If you had machines that have more cores, they just get assigned more responsibilities. There's no imbalance of performance over time. And so we think about this system as essentially ending the constant refresh cycle that customers have been on, deploying legacy infrastructure. In our case, you just feed the system like the human body. It gets bigger. And then over time, as certain cells start to age off, you eject them from the cluster, but the body lives on even though the parts are different over time. And so this becomes the basis for that core data foundation that customers can go build on. But it's more than just data, logic and data. As I mentioned earlier, we've been supporting functions for a long time. Now we're extending that functional programming environment to support an extended use of services. Today, we're excited to explain to you not just the standard protocols that we've supported from a storage perspective, things like NAS and object protocols, but also the extension of support for streaming applications, for function execution, and for running database queries natively within the system. And the state of the system is that data store that I talked about earlier that's exposed to all the machines that are running functions. And here you have events, you have files, you have objects, you have tables, you have functions, you have triggers, and then policies that become the state of the system that can be manipulated and versioned and made available to all the processing elements in that global scale that I was talking about. So really what this is it represents a dramatic reduction in the complexity of deploying data infrastructure within a customer environment. You have one machine that is designed for all of your structured and unstructured data processing such that you don't need anything else, and you have one tier of infrastructure such that you can get deep insights all the way down to the archive. Saving money is a critical component of our strategy, and unless we're building a system that can be cost competitive with archive infrastructure, it's never going to be practical for customers to deploy. So here we deploy 3 different approaches to saving infrastructure costs such that customers can now afford one tier of flash for all of their data. So it starts by embracing very low-cost flash, the type of flash otherwise used in hyperscale data centers or in standard client consumer devices, the cheapest flash that we can get our hands on. And this flash works in new and different ways that needs to be written to in a manner which isn't similar to how legacy approaches to storage have been designed to write to flash. Using that next generation persistent write buffer that we talked about earlier, we can essentially organize data before it flows down into flash, and we can categorize the blocks that we store into large RAID stripes. And we basically build RAID stripes of data that has a common life expectancy, so that as we roll data down into these flash drives, you have short-term RAID stripes, you have long-term RAID stripes. When the short-term RAID stripes, the data in them starts to expire, it all expires around the same time. The nice part about this is we can build large contiguous RAID stripes without having to rewrite data over and over within the system as a process called garbage collection. And because we can avoid that, what happens is that you can extend the utility of these low-cost flash drives for a decade, and that just avoids a full refresh event on top of the fact that we can just use very, very low-cost resources. So we're taking these resources, and we're essentially working to get more free space out of them, and this brings us to data protection. We embedded a new class of codes that we call locally decodable codes, which are much more efficient than triplication-based approaches to storing data, where you pay something in the order of 66% overhead just to protect against a drive or a block failure, and even more efficient than classic RAID-based approaches or erasure code-based approaches to data storage, where you typically pay between, let's say, 20 to 40% overhead for data protection. In our case, the invention here is to dramatically accelerate the time to rebuild a lost block or a lost device within a cluster. And when something fails within a RAID stripe, we don't have to read from the entirety of that code. We only have to read from a fraction of the code, and that fraction is proportionate to the number of redundancies. These codes can stripe today all the way up to 146 plus 4 drives, or 146 plus 4 blocks. And in this case, when something fails, we only have to read from roughly about a fourth of the failed domain. And so as a result, this is a process that can run at a fraction of the time of other Reed-Solomon-based approaches to data protection, which would otherwise make you read from all of the remaining drives within a failure domain. And that becomes impractical when you get to really wide write stripes where the probability of failure goes up. You don't want that to compound with the time to recover that is growing by virtue of the fact that you have these larger RAID stripes. What we've done is we've solved for the trade-off between overhead and the time to recover by building this new erasure code that brings the overhead down today to just 3% in terms of data protection. On top of it, once you go beyond +2 with respect to data protection, you also start adding exponents of resilience. So this is an approach that gets you 60 million years of mean time to data loss on exabyte scale data stores where you're only paying 3% for overhead. Now we've gotten a lot more free space back from our low-cost flash investment. The third and the final thing that we've done is we've basically pioneered a brand new breakthrough approach to data reduction that we call similarity. And it doesn't work like compression, which is a form of data reduction which is working at the file or the block level, but it also doesn't work like deduplication, which goes across all your files and blocks but cuts data into coarse, large pieces. In our case, what we're doing is we're basically storing data into that persistent write buffer that I talked about earlier. And as data is flowing through the system, we're running a fingerprinting algorithm against your data that kind of works like a search engine would work. And what we can do with this fingerprint is we can do distance calculation between all of the other blocks which are in the cluster. And once we find 2 blocks are close enough to each other, they don't need to be exactly the same as they would with a deduplication mechanism close enough to each other, what we can start to do is co-locate them into a logical clustering of data that we call a similarity cluster. And as data flows into a specific cluster, we're delta compressing it against the reference block in that cluster. Essentially, what happens is this pattern matching goes all the way across your data like a data deduplication engine would work, but the granularity that we look for patterns goes all the way down to just a few bytes. And if you were to visualize that, you can kind of see compression is a great way to find patterns within blocks. Deduplication is a good way to find exactly similar blocks within the system, but very poor when you have just 1 byte difference between 2 blocks. And in our case, we go global and fine-grained. And the net result is that we can essentially save customers on average around 4 to 1 on their infrastructure investment with this approach that we call similarity. And on top of it, it's also just a very, very efficient hardware implementation of data reduction that happens within the cluster, thanks to the DASE architecture. There's not a dictionary or an index that has to live in every machine that responds to the I/O requests that are happening in the system. There's a single index that's spread across storage class memory and that persistent data store that I talked about earlier that lives at the stateful layer of the system. All of the machines have global access to that information. So from a hardware perspective, it's just cheaper to implement than other approaches up until now. And so that cost savings is completely instrumental to our strategy and our thinking about the future of computing, because we've moved well beyond the transactional infrastructure era where people worry about just capturing a single event, processing it, and then moving it down to the archive. The learnings that we get both from AI and from big data, they will be created from the accumulated amount of data that customers are sitting across their entire real estate with. If you think about it, both big data and AI are essentially applied statistics. And these statistical models get better when you expose them to more and more data. So data becomes more valuable in the aggregate, and being able to process on that data in real time is instrumental to our strategy. Where can you deploy this? You can deploy it in any choice of locations from cloud to edge. At edge locations, we have a number of different partners that take our products to market. Same is true for core data centers, where you can have your choice of different platforms that you deploy upon. And today, we're also happy to announce a component of our vast data space strategy where you can now deploy edges of vast clusters, global namespaces in popular cloud platforms like AWS, Microsoft Azure, and GCP. And so now you can build a single data plane that runs across all the different spaces that you may compute in a global namespace that we build called the vast data space. And what comes from this is essentially a foundation for the next generation of computing. Functions and logic that's married with state. You can build data center scale computers, interconnect those computers all around the world, and it's infrastructure that's essentially more affordable than any approach before, more parallel and more scalable than any approach before, and simpler to manage and more resilient than anything that's ever been built before it. And so that's the vast DASE architecture, the first modern systems architecture for distributed computing that's been invented in the last 20 years. It's a system that's designed for unrivaled parallelism, even with ACID transactions, unrivaled efficiency, and unrivaled resilience at any level of scale. And this is the basis for all that you're going to learn about today. The vast data store, our data storage for unstructured data, the vast database, the semantic layer that sits on top of the data store that allows us to structure unstructured data, the vast data space that extends your namespaces all around the world from edge to cloud, and the vast data engine that brings life to your data. Thank you for watching.